In this video, I'm going to be explaining some basic concepts to solve these types of control volume analysis problems using the conservation of mass and conservation of momentum integral form equations. So we're going to need to draw a control volume that overlaps with the part of the flow that you know information about. So this is a control volume, it's a nozzle, we've got flow going in and flow going out. I'm going to label this V1 and V2 for velocity. And then I'm going to draw two different types of control volumes. One that's a square and one that follows the body itself. So the control volume following the body is always the best one to do. It's the easiest to analyze. And the body has streamlines along it. That's why the control volume following the streamlines is the easiest. So yeah, we want to be using the pink control volume for conservation of mass problems and in general. So we've got surface 1, 2, 3, and 4 for the pink one, and then surface 1, 2, 3, 4, 5, and 6. And the reason why 2, 3, and 4 are different surfaces is because the pressure at 2 is different than 3 and 4. And then I'm drawing all the normal vectors perpendicular to the surface of the blue control volume. And then this is a normal vector perpendicular to the surface of the purple or the pink control volume. And inside the pink control volume, the velocity is perpendicular to the normal vector and parallel to the body itself. So as you can see, streamlines follow the walls of the body. So you're going to make a steady flow assumption while solving these problems. Typically, that means that any time rate of change goes to 0. So in this big integral form, this term that contains the d dt is 0, making the problem a lot simpler. Then we're just left with this closed surface integral of the density times the velocity of the flow dotted with the surface vector. And that equals 0. So we've got multiple closed surfaces here with unit depth. So we need to break these closed surfaces up into open surfaces so that we can evaluate surface 1, 2, 3, 4, 5, and 6, or in the pink control volume case, just 1, 2, 3, and 4. So we're going to break this up and say that this portion of the integral is equal to the open integral of the surface 1 and I'm not going to write all the terms inside the integral for now. I'm just going to write just the integral signs, and then I'll fill it in later once we do some canceling. So we're going to have 4 surfaces, and I'm going to do the pink control volume first. So just 4 surfaces. And that equals 0. And so we can rewrite this using the assumption that density is constant because it's incompressible. We're making that assumption. And then ds vector is the same as n hat, the normal vector, times ds. And then I'm going to draw this little diagram here to explain the significance of this dot product. So when you have velocity going directly parallel to the surface, when you dot velocity and the normal vector to that surface, it equals 0. And if you have velocity that's not tangential or tangential to the surface, which is parallel to the surface, then you get well, in this case it's negative because velocity is opposite to the surface, and the horizontal component, so cosine theta. And this is it means projection of the velocity onto the normal vector. So I'm just going to move this down, and then we can simplify this equation that has 4 open surface integrals to just 2. So I just circled surface 2 and 3, and you can tell that the velocity is parallel to the surface there, meaning that the dot product of the velocity and the normal vector, when they're parallel, as I just showed, is 0. So at surface 2, that evaluates to 0, and surface 3 does as well. So I'm not going to write the contents of that surface, it's the same, and it just equals 0. And then just filling out the surface integral for surface 4. And now we have to be careful which way the normal vector is facing. For this one, it's facing to the left, so it is opposite of the velocity. So it has a negative 1 x component, and the velocity has a positive 1 x component. So that means that this is negative rho v, the double surface integral ds, because for surface 1 the velocity is going to the right, but the normal vector has a negative 1 in the x direction, so that's why it's negative. But this one has a positive 1 in the x direction, and velocity is going to the right as well. So that evaluates to positive rho v double surface integral of ds, and that all equals 0. And we know that a surface integral of a surface is equal to the area. So that's just rho v1 area of 1 plus rho v2 area 2, and that equals 0. And now this is becoming a much more familiar equation. This is called the continuity equation, and this equation comes from the integral form of the conservation of mass, making some assumptions such as it's incompressible and it's steady flow. So if it's incompressible, the rho's cancel out and it becomes like this, and it's very simple to solve. So yeah, that's using the pink control volume. But now we can prove the same thing using the blue control volume, which is a little bit more complicated because there are a few more surfaces, but a lot of them go to 0 right away, and you'll see why. So we can see that we're looking at these specific surfaces, and in the closed surface integral we have velocity, and so since there's no velocity along or tangential to these specific surfaces, this integral goes to 0 because the velocity there is 0. And now we only have surface 1 and 2. And again, it's the same surface as before, because of the way we defined the right surface to be 3 separate surfaces. Now we show that it's the same result, and we're going to get the more simplified versions that we did before using different control volumes. So in this case, we're doing the conservation of momentum, and in this control volume we are concerned about pressure. So we need to make sure that for this blue control volume that has 3 different surfaces, one that's like at the outlet of the nozzle and 2 that are like in the atmosphere, we need to assume that they all have the same pressure, because otherwise it's going to be difficult to solve this problem. But yeah, so we're going to be analyzing this closed surface integral right here, only for this video. So we can see that the pressure is perpendicular to the surface. We can see this normal vector broken down into x and y components, and we can see that on the top we can do the same thing. I didn't draw it all out, but it's the same thing, just flipped on the top. So I'm just going to start by evaluating just the top and the bottom surfaces for this video just to prove a point that they cancel, and it's steady flow, so we're going to assume that that goes to 0 and no viscous forces, so that also goes to 0. But like I said, we're only evaluating the double surface integral that contains pressure, and I'm going to write the assumptions down right here. And incompressible just means that the density is constant. And with the surface integral that I'm going to be talking about, it doesn't really matter that much. And also this fact right here is true, but is not very relevant for what I'm going to be talking about right now. In my next video, I'm going to be going over some solved problems, and then I'm going to be going through all of the steps so you can connect the dots. But these are some really key concepts. So we've got the closed surface integral of the pressure, and then when we do that, we know that the ds vector is the same as the normal vector times ds. And so when we're just looking at surface 5, we know that the normal vector is pointing down in the negative y direction, so we put negative 1 there. And so that becomes just positive surface integral of surface 5 of the pressure times ds. And pressure is constant, so that can be pulled out. And the surface integral of a surface is the area of that surface. So we have PA5. And so now let's evaluate surface 6, which is on the top, and it has a positive 1 in the y direction of the normal vector. So when we're doing this with the negative sign, because it comes from the original equation, then the normal vector doesn't cancel out that negative sign, so that term stays negative. And when you add the top and the bottom components of this integral surface equation, they cancel out. So that's why when you're solving this type of problem and you're looking at this specific component of the equation, you can write out the work and show that the top and the bottom cancel, but really you're concerned about the left and the right components because they have different pressures and different areas. So you can just ignore the top and the bottom because they cancel. So now let's look at the pink. This seems a little bit more complicated, but it's not that bad. So we've got the normal vector at an angle. And so if we write the components of the normal vector, it comes out to sine alpha, negative cosine alpha, and 0. And then we take this component of the equation that we've been evaluating, and we evaluate it at surface 3, which is the bottom surface. We do P times the normal vector, which is this component right here, times ds. And when you look at the top and bottom, well, let's just look at the bottom for now. So if we look at the bottom, we've got the x component. Okay, we're looking at the top. So the top and the bottom cancel in the y direction. But in the x direction right here, they both go to the right and they add. See, both unit vectors have a x component to the right, and then both of them have equal and opposite components up and down. So the y component of surface, the top surface and the bottom surface cancel. So yes, I'm writing this integral with the surface of 3 in this integral the way I have it written, but I'm just explaining it in conjunction with the top and the bottom so that I can show that at the end of the day, we care about the pressure times the component to the right of the surface. So when we add the top and the bottom, it comes out to a force in the horizontal direction. So it's much easier to use the blue box for conservation of momentum. But at the end of the day, you should use that and just add a force in the x direction, in the direction of the flow. And in a worked out problem, I'll show exactly where this applies and how you do it. You can just use a box control volume, and it simplifies things for the conservation of momentum problems. Thank you for listening, and I hope this helped.